Okay, so let us continue with the fifth exercise. So the fifth exercise asks us to prove that the GCD and LCM of two given integers whose prime factorizations are given have these forms. Okay, so let us start the solution. First we prove subdivision A. So let we want to prove that the GCD is of this form. So for convenience we denote this number by some symbol. Let that be D. So D equals P1 to the power delta 1 times P2 to the power delta 2 up to Pk to the power delta K. To prove that D is the GCD, we have to first of all show that D divides both A and B. Right. Now note that delta I is the minimum of alpha I and beta I. So it is less than or equal to both alpha I and beta I. We are going to use this fact. Since delta I is less than or equal to alpha I and it is also less than or equal to beta I, we have Pi to the power delta I divides A and Pi to the power delta I divides B. Why? It's because since delta I is less than or equal to alpha I, so Pi to the power delta I divides Pi to the power alpha I, and this divides A. That's why this divides A. Similarly, Pi to the power delta I divides B. Okay, now we are going to use the result of the previous exercise. So by the previous exercise, we have D divides A and D divides B. But how? How am I making this conclusion? See, let us first recall what the previous exercise says. It says that if we have three integers u, v and w, since I have already have A and B here, so I am using some other symbols to denote the integers. U, v and w such that u divides w and v also divides w, and u and v are relatively prime. Then the product uv divides w. This is what the previous exercise 4 says. Now let me write all these relations first of all to make sense of this conclusion D divides A. Here what I have k relations. This divides A. This power also divides A. Let me write one more. P3 to the power delta 3 divides A, and like that. Ultimately we have Pk to the power delta k divides A. Okay. Now, since the Pi's are distinct primes, so P1 and P2 are different primes, so that's why these powers are relatively prime. Now, making use of this relation and this condition, and using the previous exercise, from this we can conclude that this product, this divides A. Now P3 is again a prime that is different from both P1 and P2, and P1 and P2 are the prime factors of this product. So this product and this power are relatively prime. Now we make use of the previous exercise result on this relation, and this condition. That gives me this conclusion: P1 to the power delta 1 times P2 to the power delta 2 times P3 to the power delta 3 divides A. If we continue like this, ultimately we will get this: P1 power delta 1 times P2 to the power delta 2 up to Pk to the power delta k. This will divide A, but this number is nothing but D. So that's how I am getting D divides A. Similarly, using these relations, I can prove that D divides B. So this settles the question that D is actually a common divisor of A and B. Now next we have to show that if C is some integer which is a common divisor of A and B, then C divides D. So let's assume C divides A and C divides B. Okay, whenever we see this relation, we have to understand that whatever appears on the left hand side of the vertical bar, that is a non-zero integer. Otherwise this is meaningless. So for us C is a non-zero integer. Okay, now let Q be a prime divisor of C. Suppose C has some prime divisor Q. If it has, then what can we say about Q? See, Q divides C and C divides A and B. So Q has to divide both A and B. Then Q divides A and Q divides B. But the prime divisor, okay, now look at this. Q divides, A means Q divides this product. So according to a corollary to one of our previous results, Q has to divide one of the primes, right? If a prime number divides a product, say alpha, beta, then it has to divide at least one of them. Okay, it's the extension of this result. That's what I'm talking about here. So since Q divides A, Q has to divide either P1 or P2 or up to Pk. So, but the Pi's themselves are prime. So Q has to be equal to one of the Pi's. So that's the conclusion that we can draw from this line. And hence Q is equal to Pi for some I lying between 1 and k. Okay, so we have got till this. Now, fine. So what does this mean? This means that if C has some prime divisor, it has to be one of these k prime numbers. It cannot be anything else. Also, the largest power of Q equal to Pi that divides C. Okay, Q divides C means some higher power may also divide C. So there will be a largest power with a highest exponent for which will divide C. That divides C is Pi to the power epsilon I, where epsilon I is a non-negative integer satisfying this. Okay, so what have we said here? Let me just wipe this part and then continue. Here we are saying that if Q is a prime divisor of C, then there is a largest power of Q that divides C, and that largest power is because Q is after all Pi, that largest power is Pi to the power epsilon I, where epsilon I is some non-negative. We can write positive also, right, because Q divides anyway. So Pi to the power epsilon I, where epsilon I is such that this condition is true and any higher power does not divide C. That's what epsilon is. Now, because we have a condition that C may not be divisible by any prime, you see that is also a case. C may be 1 or minus 1. In that case, C is not divisible by any prime. So this whole thing becomes conditional. If there is a prime divisor Q of C, then it behaves like this. Otherwise, otherwise there is no prime divisor. So epsilon I need not be positive. It may be 0 also, and 0 is when C is not divisible by any prime. Okay. So what can we say from this situation? From this situation we can say, oh, by the way, I have to say one more thing, right? See, C has to divide A, and since in A the largest power of Pi is what? Pi to the power alpha I. That means Pi to the power epsilon I has to divide Pi to the power alpha I. That's why epsilon I is less than or equal to alpha I. Otherwise, this is not possible. In a similar manner, since Pi to the power epsilon I also divides B. Okay. So that's why epsilon I must be less than or equal to beta I. So the conclusion that we draw from these two inequalities is this. Hence, epsilon I is less than or equal to, since it's less than or equal to both the numbers, it's less than or equal to their minimum, which is nothing but delta I. Okay? But this implies Pi to the power epsilon I divides D. Why? Because Pi to the power delta I is the largest power of Pi appearing in the prime factorization of D. That's why Pi to the power epsilon I divides D. So, by the previous exercise, we have this. p1 to the power epsilon 1 p2 to the power epsilon 2 up to pk to the power epsilon k. This divides b. Now you know how this follows from the previous exercise. It follows in the same way as the other thing followed before this, right? How we get these two conditions from these relations. That's how this thing follows. Now what is C? C is, let me write like this, since C is equal to p1 to the power epsilon 1 times p2 to the power epsilon 2, etc. pk to the power epsilon k, or there is one more situation. C is minus of this, because C, according to us, C is any integer, non-zero integer that divides both A and B. C can be negative also. To account for that fact, we have to consider this case also. pk to the power epsilon k, we have C divides D. Whether C is this integer or it's negative, since this divides D, so C divides D. And that's what we wanted to show, right? C is any common divisor of A and B, then C divides D. Hence, D is the greatest common divisor of A and B, because it now satisfies both the conditions for being the GCD of A and B. Okay, one more thing about that aspect of this solution. What happens to this whole argument when C is 1, say? Then no prime is dividing C. So then what about the truth of this argument? In that case, this is vacuously true. And to account for that fact, epsilon is a non-negative integer. In that case, epsilon I will be 0 for every I. The same is the case when C is equal to -1. So we have actually accounted for everything. So this completes the proof of the first subdivision. Now we move on to the second one. For the second one, we don't have to work from scratch. Why? Because see, A and B, the way they are given, they are positive integers. So I can use one of the results that I have already proved in one of the previous exercises. I straight away write the LCM of A and B to be equal to the product AB divided by GCD of A and B, and I am able to write this simply because A and B are positive integers. Okay, that condition should be met. Now I replace each of these integers by their prime factorization expression. So this is equal to p1 to the power alpha 1 times p2 to the power alpha 2 up to pk to the power alpha k times p1 to the power beta 1 p2 to the power beta 2 up to this, divided by this, for which I already have an expression, and that is p1 to the power delta 1 p2 to the power delta 2 up to pk to the power delta k. Now I can simplify this by using the laws of exponent. I can write this as p1 to the power alpha 1 plus beta 1 minus delta 1 beta 2 minus delta 2 pk to the power alpha k plus beta k minus delta k. Now we are concerned about these exponents. Okay, since all the exponents have the same form, it's enough to consider the first one. So let us look at this, which is what if I really write what delta 1 is. This is alpha 1 plus beta 1 minus minimum of alpha 1 and beta 1. Now regarding this, there are two cases. One is alpha 1 is less than or equal to beta 1, and the other one is alpha 1 is greater than beta 1. In the first case, what is the minimum? Alpha 1. So in this case, this expression or this quantity becomes alpha 1 plus beta 1 minus minimum, that is alpha 1. So this is equal to beta 1. In this case, the minimum is beta 1. So alpha 1 plus beta 1 minus delta 1 equal to alpha 1 plus beta 1 minus beta 1. So here we get alpha 1. Okay. Now, when this is the case, what is the maximum? Beta 1, and we have it here. So this is equal to maximum of alpha 1 and beta 1, which according to our notation is nothing but gamma 1. Similarly, here the maximum is alpha 1. So here also I write maximum of alpha 1 and beta 1, which is gamma 1. So we see that whatever the case is, this is equal to gamma 1. So in a similar manner, this is gamma 2, gamma 3 up to gamma k. So this is equal to p1 to the power gamma 1 times p2 to the power gamma 2 all the way up to pk to the power gamma k. And this is what we have to show. Right, this completes the solution to the fifth exercise. Now we see the sixth one. Okay, so what does the sixth one say? Given A and B are two integers, A and B with B non-zero. On applying the Euclidean algorithm, successively, we have, okay, so how are we going to use the Euclidean algorithm? We are given two integers a and b, and one of them is non-zero. So we are going to divide a by b. So if I divide a by b, it gives me a quotient, some integer q naught, let me denote it by q naught, b, plus some remainder r1. It could have been written r naught anyway, r1, where r1 is non-negative and its value is less than absolute value of b. Note that b is a non-zero integer, b can be negative also, that's why we are taking absolute value. Now it may or may not happen that r1 is 0. If r1 is non-zero, we can carry out this process once more with b in place of a and r1 in place of b, that is we are dividing b by r1 now. Doing that, we will get b equal to then again some quotient and some remainder. where this remainder satisfies this condition. Okay, writing one more step, we will get, if R2 happens to be non-zero, then I can divide R1 by R2. That gives me quotient Q2 and remainder R3, where R3 is non-negative and less than R2. And we continue like this. At some stage we will get something like this. Rk is equal to Qk plus 1 Rk plus 1 plus Rk plus 2, where Rk plus 2 is non-negative and is less than Rk plus 1. Now you can see one thing, that these remainders are all non-negative and they are gradually decreasing in size. So at some stage they have to stop, right? After which we will get 0, because we cannot keep on getting lesser and lesser remainders at the same time having all of them non-negative. That cannot happen. Okay? This process cannot go on indefinitely. So at some stage it has to stop. So that's what is written here. Since the integers Rk are decreasing and non-negative, there is a first integer n such that Rn plus 1 is equal to 0. So this is the first zero remainder. First zero remainder means after this stage the process stops, because we cannot divide by 0. As long as we are getting non-zero remainders, we are going on dividing and getting even smaller remainders. So once we hit this 0, the process stops. Euclidean algorithm cannot be applied any further. If this is the case, then we have to, now the exercise asks us to prove this. Prove that the previous remainder Rn is actually equal to the GCD of A and B. This is what we have to prove. Okay, here we consider R naught to be equal to, that's why, okay, I have got my answer. Here I asked why I cannot write R naught here. They are considering mod B as R naught. Okay, because here we are dividing by B, so that can be taken as the 0th remainder. Okay, now we have to prove this. Now this gives us an algorithm for finding the GCD of two given integers, which does not actually involve finding factors of the given integer. We can carry out this process. At some stage it will stop, and where it stops, the last non-zero remainder is the GCD. That's what we have to prove. Okay. So what we want to show here is this. We claim that the GCD of A and B, okay, note that by the way, that the GCD exists Why? Because one number is given to be non-zero. That was the condition, right? At least one of them has to be non-zero. Now we claim that the GCD of A and B is the same as the GCD of B and R1. Okay, this is my claim. First I want to prove this. For this, what do I need to show? Okay, let us go through this. Note that the GCD of A and B by definition divides A, and at the same time it divides B because it's a common divisor. Hence, it divides A minus Q naught B, which is nothing but from here, which is R1. Okay, so now look at this. So now we have, although this need not be written, but let me just write it for the sake of understanding. So what do we have here? We have A comma B dividing B. This we already have from definition, and A comma B also divides R1. Now think of the GCD of B and R1. This is a common divisor of B and R1. So the GCD of B and R1 has to divide this according to the definition of GCD. Hence, GCD of B and R1 divides this common divisor. Okay, this is one conclusion. Like that, we will now show that this also divides this. Again, according to the definition of this greatest common divisor, this divides B and this divides R1, right? So this divides Q naught B plus R1. Naturally, since it divides both B and R1, but this quantity is equal to, I wipe that part, right? This quantity is equal to nothing but A. Hence, from this GCD dividing A that we have here and this GCD dividing B, we get GCD of A and B divides GCD of B and R1. How? Because now this GCD is a common divisor of A and B. So by the definition of GCD of A and B, no, I think I have written the wrong conclusion. Wait. Oh, here I have made a mistake. Sorry about this. I have written exactly the opposite thing. This is a common divisor of B and R1. So this has to divide the greatest common divisor of B and R1. Okay, this is a very lackluster mistake. Sorry about this. And here we will have the Just like that, here we will have the opposite relation. This is a common divisor of A and B, so it has to divide the greatest common divisor of A and B. Now I have it right. Since the GCD of A and B and the GCD of B and R1 are both positive by the definition of GCD, the relations this one and this one imply that they have to be equal, because you remember, if A divides B and B divides A, then A is equal to plus or minus B. If both of them have the same sign, then they are equal. I mean, if both of them are positive, then they are equal. That's what we have used here. So, hence the claim. Okay, so we have now proved this. So, now we plan to use this along with the relations or